Hello, everybody. This is for the course Maths 1231 at University of New South Wales. We are going to go through the solution of the question 12 related with the eigenvalues and eigenvectors. And okay, now we will, our lambda, this is what we would like to show in the first part of this question. If lambda is an eigenvalue of A, then lambda is also an eigenvalue of the matrix A prime B inverse A B for any invertible matrix B. And second, we would like to show that if V is an eigenvector corresponding to the eigenvalue lambda, and B inverse V is an eigenvector of A prime corresponding to lambda. Now, even though we are not saying explicitly, it is implicitly obvious that, that because of the definitions of the matrix multiplication and existence here of inverse means that these are like n by n square matrices that we are talking about. In that sense, the B inverse V will be a vector. So if you think that the V is a vector in Rn, if you multiply the n matrix, n by n matrix, then you will obtain again a vector in Rn. So this is perfectly logical implication. Okay, now we would like to prove that if lambda is an eigenvalue, then it's an eigenvalue for A prime defined in this way. This is what because of the definition of eigenvalue, we want to prove that the determinant of A minus lambda I is equal to 0. This is a definition of eigenvalue. Right? The roots of this polynomial, if A prime is n by n matrices, then this is a determinant gives us a polynomial of degree n. And the roots of this polynomial are defined as eigenvalues of the matrix. So that's what we want to prove. If we prove that lambda satisfies this condition, it means that lambda is an eigenvalue. Okay, now first observe that I can also rewrite A in terms of the A prime B. So if I multiply this side by B and multiply this side by B inverse, what I'm going to have is that B, A prime B inverse, right, from this side. And from this side, I will have multiplications from the left side with B, B, B inverse, A, B, B inverse from this side. Why we are so careful about it? Because we don't have commutativity. They are not abelian, they are not commute in matrices, right? Elements are not commutative in matrices in general. So the multiplying from the left and right is important. So keep an eye on the order of the multiplication. Okay, so here B times B inverse will be an identity element, and B inverse will be identity as well, identity matrix. And as we know, identity matrices are the ones on the diagonal and zeros elsewhere. It's an analog of the one in the number theory. If you multiply identity matrix with any matrix, you get exactly the same matrix. So this is by the definitions of A. We know that I will give us the A. So we can write A prime if A prime is B inverse AB, also B A prime B inverse is also A, right? This will help us when we are calculating this determinant. If we multiply, as we've done here, multiply B inverse from this side, B inverse this time. I'm not taking determinant in that moment. I'm just multiplying matrices. This object multiplied from B and B inverse from this section. And this is what the equality is. So here I have B A prime B inverse. We've just calculated this would be A, right? This is A. And from this side, lambda is a constant, so moves, lambda is commute. A constant can commute with all the matrices. Then we have identity matrix here. By multiplying identity matrix with any matrix will give me identity matrix. And B inverse is gives me the identity matrix as the definitions of an inverse of a matrix. So this is identity. So this equality is this equality. So basically the determinant of this, if the determinant of this is equal to the determinant of that, then we have done. Well, I give you some facts here, just reminded you, you know those facts from your lectures. And determinant of A times B, determinant of A, determinant of B for any matrices, A and B, which is multiplicative, of course, if we can multiply them. And the inverse of the determinant is just, can be calculated, and you will find is 1 over determinant of B. So is determinant of B inverse. So this inverse here can go outside, right? This is true for any matrix. If you have determinant of the identity matrix, determinant of the identity matrix will be 1 because you will just multiply the diagonal entries, which all of them is 1. Then you get 1, 1, 1, 1, 1, 1. It is 1. So the determinant is identity element is 1. And the identity element is B inverse for any matrices. Of course, the dimension has to match. And then by this first fact, this will be determinant B times the determinant B inverse with the second identity here. I will have 1 over determinant of B, which will be 1, right? And so I'm getting 1 on the left-hand side and 1 on the right-hand side. And this is a fact for any matrix B. So just if we get all of those, and then we always have determinant of B inverse AB is equal to determinant of A. So these are the symmetric matrices, A and this matrix, we call those matrices are the symmetric matrices. Well, they are conjugate together. I'm sorry, I'm not saying symmetric. They are conjugate together. And their determinant are the same for any matrices in A and B. So this is how it works. If you apply the first, then you can separate all of those, determinant B inverse, determinant of A, determinant of B, but the determinant are the real numbers, so you can change the order in the real numbers. When you take the determinant, it will be real. So then you will have determinant B, and determinant B inverse will be left on the left-hand side because of this factor here, the third factor here, this will give us 1. So this side will be the determinant of A left over and determinant of A on the right-hand side. If you can't see immediately, just write it down, these ones, and you will be able to see if you're not familiar with the concept very much. Anyway, so the conjugate matrices are having the same determinant. That's what it is here. Okay, what that means when I take the determinant of this and the determinant of this will give me the same number. It means that the lambda is an eigenvalue here, and I found a lambda is an eigenvalue for A prime. So that was what we wanted to prove, and lambda is an eigenvalue of A prime. Okay, and second part of this question, we would like to find out the eigenvector related to lambda. Assume that the lambda is an eigenvalue of A, and V is an eigenvector of A, corresponding to eigenvalue of lambda. This was the equation, define definitions of A prime. If we have this, by multiplying B inverse from this side, as we've done in the first part, we will be able to obtain A prime B inverse is A. Now, since V is the eigenvector, if I multiply V on this side, then I will have, because of this equality, I will have lambda V on the right-hand side, and I have still on this one on the left-hand side. Now, I would like to think of this bracket, open up the bracket, and I would like to think B inverse V and A prime. So I have a B here, and I'm going to multiply the whole equations with B inverse. If I do that, I will have B inverse, which is the identity element. So identity of with any matrix will be the that matrix. So this will be A prime. And on the other side, I have B inverse, but lambda is just a real number. Then it moves. It can commute with any matrices. So that I will have this equality here will be B inverse lambda V will be lambda B inverse V. So altogether, I have A prime here. I have B inverse V here as it is. And I have lambda here, and I have B inverse V here. This means is by definition, I just reminded here is a B vector, is a vector in Rn if we have and taking our A and B are the matrices or n by n matrices. This is a vector in Rn. Yeah. And that is an eigenvector because this is an eigenvector definition. We have A prime, we have a vector, we have lambda, we have a vector. So it means that this vector is an eigenvector corresponding to eigenvalue lambda. As I said, I mean, this is obviously here because of the matrix multiplications, because of the existence of the inverse of the B, which means if you're thinking about the A as an n by n matrices, it means that you're thinking implicitly thinking the P and also is an n by n matrices. B inverse will be n and n by n matrices, and then the V will be a vector in Rn, and the B inverse V will be a vector in Rn. So everything will fit. Everything is coming from the definitions of the inverses, matrix multiplications, eigenvalues, and eigenvectors. I hope this will be helpful, and these facts are really important for the determinants, and I believe that everybody needs to know these facts from their heart. That's the last thing that I would like to remind everyone. Okay, thank you very much for listening. Hopefully it is useful for all of you. Thank you very much.